Thank you for being here. Last morning, early, cold, so I appreciate it. Okay, let's get started. So we've discussed the last few days what the MV system is, how we can use its properties, right, and its interfaces to offer degrees of freedom for both sensing and computing. And today I want to tell you a little bit about what protocols we need to use when we want to implement quantum communications with the NV, and then what the limitations of the NV system are, and what alternative systems are being considered in solid state. Right? Again, I want to start with the disclaimer that all of the data I'm discussing is very beautiful data that is collected by other people, not me. But okay, yesterday Eugene asked you all if you knew what a quantum repeater was, and you were either shy or tired. But we saw very few hands up, so I thought I would start today with a little bit of a repetition in what I've discussed on Wednesday, earlier this week, and what exactly a quantum repeater is, and what do we need to make it work. So a quantum repeater is a fundamental bit of technology that we need to implement quantum communication. And if we think of sort of the earlier proposals of quantum communication strategies, they're always, the goal of quantum communication is always to share a quantum state between two parties, right? That's what you want to do. You want to have two parties that are separated and they share a common quantum state, right? And they can sort of perform measurements on their own bits of quantum state and gain information in that way. And the earlier proposals of sort of the BB84 protocol and so on rely on this kind of process, right? We have a node A, that's Alice, and she has a photon that is in a certain quantum state, and she can send that photon to Bob, right? So in a way, they share the quantum state, but they share it sort of in a time-stacked way, right? Alice prepares the state, and she sends it to Bob. Later proposals of quantum communication actually rely on systems like this, which you may have seen sort of at least schematics before, where we create a quantum state over here in the central node. This can be an EPR photon pair, right? So it's a photon pair that is in a Bell state, and we send part of that quantum state to Alice, part of that quantum state to Bob, right? And now Alice and Bob, they share this quantum state. They each have a part of that quantum state, but these two photons are entangled, right? What's the challenges for implementing that? Well, one of the main challenges is that if you're sending photons through long distances, you would typically do that through fibers, right? Or through space, and even though the probability of a photon interacting with something in your fiber or with something in air is small, if you're sending that through long distances, eventually you're going to have losses that kind of forbid the protocols that you're trying to implement, right? So when you're sending photons through a fiber, these photons are absorbed or they interact with the fiber, and the probability of them arriving at a later node decays in an exponential fashion. Right? And if this was a classical signal, so if I were dealing with lots of photons, I could put a repeater in between, right? So I could have some implementation of an amplifier here that would sort of check what the state of this light is, and then amplify that signal before it arrives to Bob. But when we're talking about quantum mechanics, that's not possible, right? Because of the no-cloning theorem, what happens is I cannot, in order to check what the state of this photon is, I need to perform a measurement. And if I perform a measurement, I collapse its state, and I can no longer sort of copy this information and send it to Bob, right? So what kind of solutions are there? Well, the solutions that are proposed are reliant on mechanisms of this sort, right? So now I can take my entire quantum channel over here, this long piece of fiber, and I can break it down into two parts and have two sources of entangled photons instead of just one. And by performing a Bell measurement here in the middle, between photons, between this photon and that photon, right, I can perform a Bell measurement of the state of these two photons in this intermediary node over here. And this Bell measurement actually projects this entanglement onto this photon and that photon, right? So by performing this measurement in between, I now can entangle these photons at the ends over here, and nodes A and D can now share this quantum state, but photons have traveled through much shorter fibers, they're thus much less susceptible to interference through their path, right? Yeah?
So is that enough? And so does that give you already better fidelity between A and D, or do you need to go through distillation and memory?
You may have to go through distillation. So that's what we're getting to. It depends, right? This is technologically challenging as well, because you need to have these two photons arriving at the same time. And I'll show an example where that's the case, where you don't really need to distill. You still have a conditional entanglement of projection between your memories, but it kind of depends on how much your losses are through the fiber and how effective this process is, right? And that's the two figures of merits that you need to consider. But it will become clearer a little bit as we go along. So if we're thinking of a quantum network, where for instance we want to share a quantum state between node A and node H over here, we can think of sort of stacking these bitwise channels, right, in a way where we eventually can sort of close this loop and we can send sort of in a stepwise manner, we can send this entanglement information, right, between these two channels. Now, I think I mentioned this on Tuesday, but exactly what you need, right? So there's a few technical challenges over here. The first challenge is the following. If I'm sending this photon that way and that way, right, and I'm performing a Bell measurement over here, this Bell measurement is typically reliant on these two photons interfering, right, in some type of interference process, right? So that means that these photons have to arrive simultaneously, right? And doing that through fibers can be hard, right? Your fibers can sort of expand depending on their temperature and so on, and that can change the arrival times of these photons. Another piece of sort of another element that you need in this network is an element like this, where you have quantum memories, and that's what I'll tell you a little bit more about today. It's this type of element over here, right? Where I have quantum memories, and these quantum memories can send photons to this intermediary node. We perform again a Bell measurement over here, and in that way we can entangle these quantum memories, right? And we can sort of become less reliant on having these processes being synchronized, right?
Can I re-ask you?
Yeah.
So even in the ideal case,
yeah,
we have two cases: either one fiber that is twice that much long, or
yeah,
two fibers that are at an ideal Bell measurement. Is it better to have two shorter fibers and the ideal Bell? So do you get better fidelity?
If you have that ideal fiber, if your fiber has no losses, no.
No, not ideal fiber,
Okay.
ideal Bell measurement. Ideal swap.
You still need to distill, right, your entanglement. So there's still a loss that is associated with this process. And then again, it depends on how big that loss is compared to your fiber. Yeah, we can discuss it. Okay, so what concepts we're going to need before we move forward today? I thought it's early, it's cold, I would start from the basics, but you've probably all seen this before. One of the processes that we're reliant on is this interference of two photons, right? And can I see a raise of hands of people who are familiar with this process? Okay, good. Now we're talking. So, of course, if you come with a photon from a beam splitter, right, you have 50% of chance of going one way or another way. So your outcoming state looks a little bit like this. If you're coming from the second arm in your beam splitter, then because this mirror in your beam splitter is not identical, both faces of it are not identical, you gain a phase factor over here, right? If you're coming with one photon from one arm, one photon from the other arm, your final state looks a little bit like this. And if your photons are indistinguishable, right, so if I cannot tell what photon is what, then my final state becomes this, right? If I come with two indistinguishable photons onto this beam splitter, and they arrive at exactly the same time, they have the same frequency, they have the same wave packet, then both photons will either go one arm or another arm. Now, because my detectors are quantized as well, I can only see one photon at a time, right? So if I'm doing a measurement here, I will never see two clicks at the same time in these two detectors because both photons went one way, but I'll only see one click, right? And if my photons are not indistinguishable, then of course I can see one click in each detector arriving at the same time. The other concept that we need is the concept of what a projective measurement is, and after this block of lectures, you all know how this looks like, right? If I have a quantum state and I perform a measurement, then my wave function collapses, and in the case of a simple entangled state like this, that just means that by measuring one qubit, I gain information about the other one, or I know exactly what the other one, what a measurement on the second one should be, but that doesn't have to be the case, right? You can project on a subspace and have sort of a superposition here of my wave function once it's out. And then the last thing that we need to remember about is what the NV looks like, right? So this is what we've discussed earlier this week. This is a system that has a ground state with a spin, an excited state with a spin. It has optical transitions. And the important bit that we'll need to remember today is that if I look at these direct ground to excited state optical transitions, there's selection rules that actually give me very clear spin-dependent transitions, right? So I can drive specific optical transitions depending on what the spin state of my qubit is, right? And that's one of the features that are going to be useful in our discussion today, right? So the first experiment that I want to discuss today is the earlier implementation of distributing entanglement based on these qubits, based on the NV center in diamond, right? And it's a protocol that depends on heralded entanglement, right? So it depends, I only establish entanglement conditional on a certain measurement that I've performed. That's what this means, right? So I run a certain protocol on the NV, and I run it repeatedly, and I know that conditional on certain measurements that I perform, then entanglement has been established between two qubits or not. Right? So the setup that the authors used to implement that looks like this, and we'll go through it in a sort of a stepwise fashion. So first of all, they have two NVs, right, that are in two diamonds and two cryostats that are separated. In this case, they're in the same lab, but they did not have to be. Right? So each NV is in one of their cryostats. They have for each NV a microwave circuit that they can use to apply these microwave pulses and control the spin state of this qubit. Right? So this microwave circuit is used to control the spin configuration of each of these qubits. Right? And they have a set of control lasers and optics that they can address, with which they can address optical transitions from each of these qubits, right? So they have a red laser for each of these qubits. This red laser is this resonant laser over here, right? So it drives resonant spin-dependent transitions between ground and excited state. They have a green laser, which is what you typically use to talk to NVs in their photo sideband, right? So they can also look at the NVs without driving resonant optical transitions. Each NV has an independent, or is controlled by an independent set of lasers over here, right? And then they have a common red laser over here, where they can send optical pulses to both NVs at the same time, right? Now, in the outcoming path, right, so this objective over here collects the light that is emitted by the NV, collects photons that are emitted by the NV, and it sends it through these fibers, right? And in the outcoming path, the important part is that we have, of course, a set of polarization optics, with which we can adjust, right? So that the polarization of the photons that are emitted by either NVs is the same, right? So that we can make these photons emitted by each of the NVs indistinguishable. And then we have a beam splitter over here, right? And that beam splitter is then connected to two detectors and sort of the typical photo interference setup that you would see. In what follows, I'll denote the state of the NVs by spin up and spin down with the subindex that is associated with each NV. And then in terms of photons, what we're interested in is a photon number state in these fibers, right? So what we're probing is whether there is a photon or not going through these fibers. And that's kind of, sort of the experimental schematics of what we need to sort of probe distribute entanglement between these two NVs, right? So the protocol looks a little bit like this, right? We have a optical pulse that is relatively long over here. This pulse just initializes the spin, so it guarantees that I start off from a well-defined quantum state for both NVs at the same time, right? So now I'm running this experiment in parallel in the two sort of qubit systems. So the state that I start off with looks a little bit like this, right? Or looks like this. I have both NVs with their spins pointing up. Now, what I do is I use one of these spin gates that I introduced in the last lecture in order to create superpositions of the spins, right, for each NV independently, right? So I put each NV in a superposition state, so in a plus X state. Now, the next step is where I actually create spin-photon entanglement for each of the NVs independently, right? So what the authors do is they take this laser, and now instead of doing a long pulse, they do a very short pulse. They actually make sure that this short pulse, its length, it's smaller than the lifetime of the excited state of this NV, right? So that at most, you're going to get one photon from these NVs, right? So they make this pulse very short, they excite this transition, and through excitation and relaxation of this sort of spin-conserving optical pathway, then the NV emits a photon. So now what I have is that each NV independently is entangled with the photon number state in the fiber, right? So the spin up part has emitted a photon, the spin down part has no photon associated with it, right? So the total state of my system is now just the product of these two states for each NV independently. So far, each NV is entangled with the photon, but there's no correlation between the states of the two systems, right? They haven't interacted, I haven't brought them into proximity, they know nothing about the existence of the other qubit, right? So what they do at this stage is here, they realize a projective measurement, yeah, on the photons. What do? They look at the interference process over here, right, in this beam splitter, and they look at cases where they measure a single photon in one of the detectors, right? So that's where the heralding comes in. From here on, they'll only continue the experiment provided they've measured a single photon. Yeah. So that's the first part of the heralding, of the conditional part of this experiment. Right. So if you remember your two-photon interference, in order to measure a single photon in one of the detectors, there's three options that are possible, right? Either a photon came in from arm B, or a photon came in from arm A, or a photon came in from each arm. So my projecting operator, if I see a click in the left detector, looks like this, right? Either this situation, or that situation, or this situation will give me a single click. If I see a click in the right arm, then there's a phase factor over here, but the projector looks largely similar. Right? So now if the state before this projective measurement looked like this, when I act on this state with these projectors, what I'm getting is something like that, right? So either my two spins are up, in my state, in my coherent superposition, I have components with two spins up, or one spin up, one spin down, right? And then this sign depends on whether the left photodetector or the right photodetector clicked. Now, if I look only at the spin part, I've measured my photons, they're no longer important for the story. If I only look at the spin part, the state that I have left after this projective measurement has this shape. Now, if you've paid attention to Anna's lectures and Ona's lectures, this is an entangled state, but it's not a maximally entangled state. Right? So how do I get there? Right? How do I keep this protocol running in order to obtain a maximally entangled state? Well, the idea now is something that we use, and it's going to show up repeatedly in the rest of the story, is the following. I now just flip my spins, and I repeat this photon entanglement process. Right? So what I do is, if my state before the measurement looked like this, I realize my projective measurement, I measure a photon in one of the detectors, and provided that this measurement is successful, I move on, right? The state of my spin then looks a little bit like this. After I flip these spins with the pi poles, right? So I apply a pi poles that only acts on the spins, again, simultaneously for both qubits. I flip my spins, they end up spin down, down, up, down, down, up, and I realize this photon entanglement process again. Right? So I again come in with this very short optical pulse, the system gets excited, de-excited, it emits a photon that depends on the spin state. Right? And at this point, you can imagine what I'm going to do, or what the authors did, is they do a projective measurement again. Right? So now, the story is the same. Once they perform this projective measurement, the state that they end up with at the end is the following state. Right? So either spin down, NVA has spin down and NVB has spin up, or NVA has spin up, NVB has spin down. Now, this is a Bell state, it's a maximally entangled state. So what the sequence of measurements, conditional on the fact that I've measured a single click at this step and a single click at that step, what this sequence of operations did is it placed my two NV states into this Bell state over here. Now, the last step is just to check that, so to make sure that this protocol was successful, and then you do that through a readout step, right? That is just what I've been discussing since Tuesday, right? So at this point, they have a well-prepared quantum state over here. This is a Bell state, right? Yeah. Sorry? Oh, sorry.
I have a question about this projective measurement. You said measure a single click, but the part with 1-1 where the two photons come in and go out one arm. Why is this a single click?
Sorry?
The third part of the projector.
Here.
Yeah, why is this a single click?
Because this detector it can only see one photon at a time, right? So it's a single photon detector. So if I come in with two photons, it knows no difference from that and the single photon case. right? My detector is, so these APDs are quantized in a way that they can only see one photon at a time. After they click once, they have a certain dead time. So if I come in with 2 photons, it will just miss the second one.
Okay.
Yeah? So the detector knows no difference between this situation and that situation. It cannot tell them apart. Right? And that's just because of the mechanisms of this single detecting photon process. Single detector photon process. So, and that's sort of at the core of these protocols, right? It's the fact that you can't tell this situation apart from that situation in terms of what you measure. Right. Okay, so yeah, so maybe just to recap. So this is a relatively long protocol, right? It's a multi-step protocol in order to prepare the entangled state. That's what this is doing. It's saying, I start off with 2 NVs that are separated. They don't know about the existence of each other, but I can perform certain operations on each qubit and then interfere the photons that they're sending in order to put these 2 NVs into an entangled state, right? And then after I have this entangled state, then I can just go through my operation loop, right? So I can apply microwave pulses, and I can read out the spin of the system through optical transitions in order to measure, right? In order to test what the state is. And that's exactly what the authors do, right? So they have the possibility of applying a microwave pipe over 2 poles here that allows them to measure in the base X. Right, so this microwave pulse rotates the spin, and it allows them to measure the spin projection on the base X, and they can do that independently for each qubit, right? And if they want to just measure in the base Z, they just apply this laser pulse, and they detect photons over here, right? And because of this photodynamic circuit, because of the photodynamic rates of the MV, you know that either you detect photons if the qubit was in spin up, or you don't detect photons if the qubit was in spin down. Okay. And they do that independently, right, for qubit A and for qubit B, and they look at the correlations, right, so they perform quantum state tomography, they look at the correlations for measurements of spin up, 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 down, down, up, down, down, and what they see is if they measure in the Z basis, then they have strong correlations for measuring up, down, or down, up. That's what you would expect from this Bell state over here. If they then rotate the spins and they measure in the X basis, then they can put the system into the other 2 Bell state bases, right? Basis states, right? So up, up, or down, down. Right. So this is, I mean, this has been it's a 10-year-old result by now, but it's at the basis of all the following protocols that have used entanglement based on the NVs, right? Whenever you're talking about preparing entanglement for NV centers, then that's the type of protocol you're running. But it's all nice and well, but it's not the end of the story, right? Can we use this preparation of entanglement then to realize teleportation of a quantum state? So to teleport a quantum state into a quantum memory? And the answer is yes, and I'll show you how this has been done. But first, let's just run through a typical teleportation protocol, right? What are the ideas and what do we need to make that happen? Right, so, provided that qubits A and B are entangled, right, and Alice has qubits A and C, Bob has qubit B, the starting situation here is this, right? So qubits A and B are entangled, they're in one of the Bell state bases, for instance. It could be this, psi plus, but it could be any of the other Bell state bases. And qubit C is in the state, right? It's alpha 0 plus beta 1. And the goal is the following. I want to transfer this quantum state to the state that Bob has, right? So I want to take a quantum state that Alice has, and through this entanglement, Alice wants to send this quantum state to Bob, right? Now, if I look at the full state of the system, at the start, it's the tensorial product between these two states, right? You can rewrite it like this. And now I can rewrite this starting state, right, as this guy, right? So now this is written in terms of the Bell state basis, right, for qubits A and C, times some superposition of qubit E, right? So now if Alice performs a Bell state measurement on qubits A and C, she knows what transformation Bob needs to perform to his quantum state in order to recover the original quantum state of Charlie, right? So that's what the protocol looks like, right? So Alice now measures her two qubits, A and C, right? It could be in the Bell basis or it could be in another basis, and she does her own transformation to it. And then she feeds forward what unitary transformation Bob needs to perform to get back Charlie's original state. Now, one of the sort of most better known implementations of this protocol is, of course, Zeilinger's implementation, where he established sort of this teleportation from the islands of La Palma and Tenerife in the Canary Islands, right? So in this implementation, what he had was an EPR photon source over here, right? So this is a source of entangled photons. He sent one photon to Alice over here and one photon to Bob, all the way out in Tenerife, right? And then Alice got another qubit from this arm. And by performing this Bell state measurement over here, she could then inform Bob about what kind of operation he needed to do in order to transform this qubit that was arriving into a qubit that had the same information as this original one. So this is, I mean, a very important implementation. But of course, if I want to now use the quantum state that Bob has in this photon, I either need to use it immediately, or I need to find out a way of actually writing the information of that photon into some memory, right? Of storing the information in that quantum state. And that's what these solid state systems are sort of trying to do, right? They're trying to use this entanglement, but now to transfer information between qubits that are good quantum memories, where you can store that information for a certain amount of time. And they're using this process of entanglement generation that we've just discussed over here to do that. So how does that experiment then work? Now I have two nodes, right? I have Alice's node over here, and I have Bob's node over there. Alice has, of course, its own electronic qubit. Bob has an electronic qubit. But Alice has an additional qubit, which is a nuclear spin qubit. In this case, it's a nitrogen nucleus, but it could be just as well a carbon nucleus or another qubit. Right? And what Alice is trying to do is it's trying to transfer the information of this nuclear spin qubit onto the quantum state of Bob's qubit. Right? Now, the operations that we have available, and you've seen cycles like this throughout my presentation today and in past days, are the following. I can use microwave to drive electronic spin transitions, right? So I have any type of arbitrary rotation on the electron spin available to me through the application of these microwaves, right? I have readouts of the electron spin available, right, through these optical transitions and the same implementations we've discussed. And I have a conditional rotation on the nuclear spin available, right? So I can apply an RF field that talks directly to a nuclear spin. But again, because this nuclear spin splitting depends on the electron spin, my RF is either resonant or not resonant with the nuclear spin rotation, depending on what the electron of the depending on what the state of the electron spin is, right? So this is now a conditional rotation on the nuclear spin. If my electron is in spin in state 1, my RF is resonant and it can drive rotations of the nuclear spin. If my electron is in spin in state 0, now my RF is no longer resonant and I cannot drive rotations of the nuclear spin, right? So those are the operations I have to play with. So how can I use these operations to build a circuit that allows me to teleport the state of this nuclear spin onto that electron spin? Now, the start of the protocol is, if you remember, it assumes that qubits A and B are entangled. So the start of the protocol is, of course, I need to establish entanglement between the electron spin of Alice and the electron spin of Bob. And the way to do that is exactly what I've discussed in the first half of this presentation. Now, the next step is that Alice performs a Bell state measurement on her two qubits, right, on the nuclear spin qubit and the electron spin qubit. She then sends this information to Bob, and then Bob can adjust his quantum state based on that information he received from Alice. Right. So the first requirement of my protocol, I start off assuming that I have this entanglement, right, that I have implemented this. And then the first step is I prepare the state of my qubit 1, right, of the nuclear spin qubit. And I do that through these conditional rotations on the nuclear spin, right? These are the RF manipulation pulses of the nuclear spin, combined with a rotation of the electron spin of Alice, right? The state of my qubits at the end of this operation is this guy, right? So my qubits A and B are in one of the Bell states, right? And then qubit C is in the superposition with these coefficients, which is what I want to inform to Bob, right? What I want to send to Bob. In a typical implementation, or if you're looking in sort of quantum information terms, what a protocol for this teleportation looks like, what I would do is this. I would do a C0 gate, right, on qubit 1. And then a Hadamard gate on qubit 1, and then I would measure these two. That's what the Bell state measurement protocol looks like if you're just looking at your simplest quantum circuit, right? But I don't have these operations available, right? These are not the operations I have. I told you I can do arbitrary rotations on the electron spin, I can read out the electron spin, and I can do conditional rotations on the nuclear spin. So I actually don't have access to this Hadamard gate on my nuclear spin, and I don't have access to this readout, direct readout of the nuclear spin. So in order to do that, what I need to do is I need to map these operations onto combinations of the operations that I do have. And then my quantum circuit looks a little bit like this. I can perform the C0 gate, that one I have access to, and then I can sort of map this Hadamard onto this combination of pulses on the nuclear spin and the electron spin, right? So I rotate the nuclear spin, rotate the electron spin, rotate the nuclear spin in a conditional fashion. And then my measurement step is always done on the electron spin, right? So this combination of microwave pulses gives me a Hadamard. So it places my combined system into this state. And then the measurement protocol is now done. First, I measure on the electron spin, and then I perform a certain number of operations that allows me to map the state of this electron spin, of this nuclear spin onto the electron spin, and I read out the state again, right? So that's the kind of sort of ingenuity that when you're working with these things in the lab, you need to start thinking about, right? It's how do I map these operations that may look simple in paper, how do I map them onto the operations that I have accessible, right, within my experimental setup. So now at the end, of course, I have one of these 4 different possibilities. So I've either measured, oh, this is wrong, I forgot to flip this guy. I've either measured state 0 and state 0 in this sort of stacked process over here, and I have this state, or I've measured 0 and 1, and I have that state, and so on and so forth. So now, depending on the results of the measurements that I got for the state of this electron spin over here, I can then tell Bob what he needs to do to his spin in order to recover the original state of the nuclear spin, right? So now I can feed forward that information. Bob performs a unitary and measures on its own spin, right? Now, here I want to recover something that I mentioned last time on Thursday, which is the following. In the meantime, so while Alice was doing these measurements on her own qubit and so on and so forth, it may look like Bob was doing nothing. Well, actually, Bob was doing a dynamical decoupling, so it was continuously applying microwave pulses to its qubit in order to prevent this qubit losing information or interacting with its environment, right? So whenever we're talking about doing nothing, actually what we're talking is this, right? What we're saying is this. I need to be continuously interacting with my qubit in order to avoid its loss of phase coherence to its environment, right? Now, if they plot the teleportation fidelity of this protocol, then they can demonstrate that this teleportation happens in a successful fashion, right? The next thing I want to mention is the following. When we're talking about qubits in this case, for instance, we have 2 electron spins over here and 1 nuclear spin. Interacting with these electron spins is relatively fast. Right, so I can apply gates on these electron spins on the order of 50 nanoseconds or so, which looks really fast compared to its own coherence time. The coherence time of these electron spins is typically, if you pull these things down, it can be up to 1 second or 2 seconds or that order of magnitude. So you can say, well, the coherence time of these qubits compared to the gate time that I have for these qubits is really long, so I'm performing very well, right? It's a nice system to work on. But remember that in between, if I want to do that, I need to also apply gates onto the nuclear spin. And now the gates that I need to apply on the nuclear spin are a lot slower, right? So they're on the order of 100 microseconds. And that just comes from the difference of the magnetic moments, right, of the nuclear spin and the electron spin, right? My electron spins interact a lot more strongly with oscillating magnetic fields than my nuclear spins do, just because of the difference of the magnetic moments, right? So in between, while I'm sort of focusing on the states of these qubits here that are related to the electron spin, I also need to implement operations on the nuclear spin, right? And these are slow. So that means that actually the time scale that I need to be worried about is not the coherence time of these electron spins compared to their own gates, right? But it's the coherence time of these electron spins compared to the longest gate that I need to apply in my system, right? And that rate is a lot less forgiving. Right, so it's still very important to work on systems that have very long coherence times. Now, these type of protocols have then, right, this is an implementation of 2014, and since then there's been multiple, right, sort of follow-up works based on these systems. We've seen sort of tests of Bell inequality in setups that had much longer spatial separations, right, in a way to show loophole-free operation, right. We've seen multi-node networks established based on the NV, right, and we've been, or they have been able to teleport qubit information between non-neighboring modes. Right? So what's the problem? What's the limitation for these systems? Well, it all starts in this entanglement step here. Right? I told you that this is a heralded entanglement generation, right? So I rely on being able to detect these 2 clicks on my 2 different detectors. And if I look at the success rate of this entanglement generation, it's actually rather small, right? I need to be able to initialize the nuclear spin and then entangle my 2 electron spin qubits. The success rate of this operation over here is about 10 to the minus 7. After I tried a few times, then my whole system has lost its initialization, so I need to start over. So there's some serious experimental limitations to the success rate of this process. And at that time, it was about 1 over 250 seconds. So within an hour, you can maybe get a handful of entanglement events, right? But that was really the limiting part of your experiment. Right? That's hard to establish. So why is it so hard? Right? What's at the core of this limitation? So first of all, is that I've shown you this optical spectrum of the NV a few times now, right? And we've discussed it sort of at length on Tuesday. But the first part is that only about 10% or less of the photons emitted by the NV are useful for entanglement, right? And in this entanglement protocol, you have 2 types of optical interactions. You have this one, which is used for readout. There, I can basically use any photons. I can, as long as I detect a photon, I can tell that it was either in spin up or spin down. But these steps over here, remember, I rely on being able to interfere the photons that are emitted from the 2 NVs, right, in a beam splitter. So these photons must be indistinguishable, and when I say that they must be indistinguishable, what I say is that they must come from this sort of coherent optical transition over here. So this optical transition that is not coupled to any photons, right? And the probability of getting photons actually in this transition is limited to about a little bit less than 10%. Right? The second challenge is that diamond is in some ways a hard material to work with for optics, right? Getting photons out of diamond can be very challenging. So the refractive index of diamond is really high, which means from the photons that the NV emits, a lot of the photons just get trapped in the diamond and they bounce around between the facets of the crystal and they never come out, right? So I'm not able to get to them. So what's one of the proposed solutions to that? Well, one of the proposed solutions is working with cavities. So developing cavities, optical cavities on diamond that could, first of all, enhance the rate of photon emission into this region of the spectrum through the Purcell effect, right? So I would build a cavity that is kind of matched to that frequency, and then that would enhance the photon emission into this, this optical line over here. And additionally, developing these cavities could enhance the collection of photons because it could channel now all my photons into a directional mode, and I could make sure that I'm getting all the light out that I can from this system, right? And that's something that people have pursued sort of for the last 10 years, I would say. So this photo is actually of the device they used in both of these experiments that I've shown you today. And what that is what we call a solid immersion lens in diamond. Right, so this is the NV is sitting here somewhere at the focus of this lens, of this dome, and then you can process diamond through milling of the material, right? And you can create this lens structure that directs light a certain way, and it also helps with matching the angle of incidence of the photons that are emitted from the diamond in order to get all the light out that you possibly can. And this is a sort of a comb of waveguides of diamond that have emitters in them, right? So these are the kind of structures that people have been looking at. Now, the NV in particular is not good for these solutions, right? The NV, I told you the first day that it's a low symmetry system. It has this C3 rotational axis over here, and it has this electronic configuration, and what that means is it has a permanent dipole. Right? It has a permanent electric dipole. What that means is that whatever electric noise I have around is going to degrade the optical properties of the NV. Right? The NV couples, the optical transitions couple to all of these electrical noise, and it sort of makes your optical transition line wander around. It degrades the properties of these emitters. So there's been a lot of effort in the last 10 years or so in developing these structures, and that's all very useful effort, and I'll show you why. But what we found is that the NV is perhaps not the ideal system for these type of applications, right? Challenge number 3 is more related to what the protocol looks like. So this protocol I've shown you relies on being able to synchronize the photon emission from these two NVs. That's technologically very challenging, right? So what are people looking at? People are looking at alternative platforms and protocols. And one illustration, and there's many of these around, right? There's sort of pick your choice. But I think one of the very interesting implementations of that is kind of summarized in this figure, which is from this paper last year. This is a paper from Lookin. The reference is right there. But this is an illustration of what types of analogous systems people are looking at and what types of different protocols people are looking at. And I'll walk you through it in a little bit more detail. So in terms of analogous systems, people have been, the idea of having these things in the solid state is still very tempting, right? The solid state, it's in a lot of ways easier to work with and to integrate into devices and so on and so forth. So a lot of people have been looking at alternative defects, so systems that are analogous to the NV, right, but that have differences in important ways. And one of the types of alternative systems that have been looked at are also in diamond, right? So this is another defect that is in diamond. In this case, it's a silicon vacancy, but there's other groups in the world that are looking at the same class of defects. We call them group 4 defects. So this is silicon vacancy, tin vacancy, germanium vacancy, right? So these are defects where we have the atoms of the group 4 in the periodic table. Silicon, germanium, tin, in the diamond lattice, right? So now we have this impurity over here sitting between two vacancies in the diamond lattice, right? What's so special about this defect? Well, it has an inversion symmetry point, right? So now if you trace, if you take this point here, halfway between the vacancies, and you trace the inversion, you can see that this defect is inversion symmetric. What that means is that it doesn't have a permanent dipole, right? It doesn't couple to all this electric noise. It's largely robust to electric noise that is around, but it also means that it doesn't couple to phonons very well, right? So now most of the light that this system emits is in this interesting region of the spectrum. All of the light that comes out, all the photons the system emits, are very weakly coupled to phonons, so my phonon-coupled emission is kind of disappearing as I cool down the system. Yeah? So all the phonons are useful phonons. All the photons it emits are useful photons. It also has a very natural access to a nuclear spin register, right? Because this group 4 atom over here can have a nuclear spin, and in that way you have this electron spin that couples to light, right? There you have these optical transitions. But this electron spin also couples relatively strongly to the nuclear spin of the group 4 impurity that is sitting here in the middle. And now you can use microwave pulses to control the electron spin and RF pulses to control the nuclear spin in the same way as I've discussed the past couple of days. So this that has a nuclear spin register that is available. It's a high symmetry defect. That means it has low coupling to photons. The caveat is that this type of systems must be operated at very low temperatures, often sub-Kelvin temperatures, right? And that's because of their electronic structure. There's an orbital degree of freedom over here that you want to freeze out. So if you're operating with these, you need to cool them down. Now, an important consequence of this system being so robust with respect to spurious electric fields and so on is that you can put them into cavities, right? So now you can structure your diamond and put the system inside. When you're doing that with the NV, for instance, if the NV is sitting very close to a surface, then it's very much sensitive to the surface dynamics of the diamond. But because this system is robust to this type of interaction, you can now place them into a cavity, and you can start thinking of alternative protocols. And that's what the authors of this work have done, right? So they built a photonic cavity made out of diamond. So they nanofabricate on this diamond to build a cavity, and they place this defect here inside of the cavity. And they build the cavity in the strong coupling regime, where what happens is that the reflectivity of this cavity is directly related to the spin state of the system. Yeah. So now the cavity will either let a photon through or reflect a photon, depending on what state, spin state I've prepared my qubit, my solid state qubit in it. Right. So that's what is reflected in this part of the figure over here. Right. So you have the reflectivity over here, and then you have the probe frequency, and depending on what spin state I've prepared my system in, the reflectivity jet will be at one frequency or another, right? So that's what's kind of summarized over here. If I come in with a photon and my qubit is in a spin up configuration, my photon will be reflected, whether if I come in with a photon and my qubit is in the spin down configuration, the photon will be transmitted. So now I can use this reflection-based process to establish spin-photon entanglement, and I won't go through it in a lot of detail, but the idea is this, right? I can, again, initialize the spin, right, and prepare it in a coherent superposition. That's what these two steps do, right? So I initialize into a well-defined state, and I come in with the microwave pulse, and I prepare my electron spin in a coherent superposition. And now what I do is I send photons, right? I send photons in two steps. So I send a pulse, and then a time later I send a second pulse. This pulse has few photons, right? But it doesn't have to be a single photon. All that matters is that they come with a certain separation, and I can apply a microwave pi pulse to my spin in between, right? So now my photonic state is encoded in the time of arrival, right? So this is an early, late timing type of photonic state. And I can entangle this early, late information with the state of the spin, right? So if I've prepared my spin in this coherent superposition, after I come in with the first pulse, I end up in this state. Right. So, my photon state is described like this, right? So I have a certain coefficient times an early arrival plus another coefficient times a late arrival, right? And after I come in with these two photon pulses and an intermediary pi pulse over here, the state that I end up with is this guy, right? So I have a spin up coupled to a late photon, and a spin down coupled to an early photon. You can do the same type of math that I've shown throughout this talk until here in order to get to this state. Right. So now I can use this fact that I can sort of use this spin-photon entanglement gate. This is what represents my entire spin-photon entanglement gate. And I can use that in order to distribute entanglement between these between two of these qubits that are remotely separated, right? So now I have qubit in node A in its own cavity. I have qubit in node B in its own cavity. I can come into my system with these two photon pulses. It will either get reflected or transmitted through this cavity, so it comes down this way. And then I send these two photon pulses, which now are entangled with the state of this qubit. I send them to the second qubit. It comes in, and it interacts with the second qubit and gets entangled with that second qubit, right? And then in order to perform a measurement, I send these photons to a time delay interferometer, right? In order to erase which way information from these photons, right? So that's what's sort of represented in this circuit over here. I come in with my photon or photonic state with early and late arrival times, right? I perform this electron photon entanglement gate. My photons go on and then interact with node B, and this entanglement gate is again done, right? And then I measure my photon state, and that projects the two spin qubits into an entangled state, right? Now, this protocol has a few advantages compared to what I've shown previously. So the first of them is that I'm no longer dependent on synchronizing the photon emission from the two stationary qubits, right? So now I just take my photons and they first interact with the first qubit, they then interact with the second qubit, but there's no sort of sophisticated synchronization that I need to perform, right? The second advantage is that now I'm encoding the photon information into an early or late arrival times, and these degree of freedoms are somewhat more robust to polarization fluctuations inside of the optical fiber, and so on and so forth, right? Now, how much better does that make this protocol compared to the previous one? If you look at the stage fidelity that you can prepare your entangled electron spins in, right? That's about 0.8, and that starts decaying if you operate the system faster in order to enhance your success rate. The 1/250 seconds of the NV system was somewhere over here. So you can still demonstrate fidelities when you're operating an order of magnitude faster, maybe a little bit more, right? This is exactly the protocol that they used in order to demonstrate entanglement over this citywide fiber network in Boston last year, right? That's exactly what they've used. And of course, I mean, these systems, the NV has about 20 years of history being studied on, and a lot of what we've learned from the NV, people are using to improve on these protocols, right, based on alternative systems. So there's some way to go here in improving the success rate. Other systems that are being studied, and here I'll just mention them very, very, very briefly. I've done some work, and I'll talk about this next week if you're still here. I've done some work on alternative systems in other crystals like silicon carbide that have optical transitions directly in the telecom band. So these systems are interesting because you could take the photons that they emit and just send through fibers that are already available and present. Right? There's other defects in silicon carbide that are being studied, defects that have symmetry properties that make them robust to interactions with electric fields as well. So there's a large variety of candidates in crystals in analogous systems. In the past year, there's quite some work being done on defects in silicon, right? And of course, working with silicon has right, it's in terms of industry implementation, it's very, very tempting. And silicon, despite being a crystal that has a relatively short band gap, so it doesn't really have a lot of optically active defects that are available, it does turn out to have some defects that are optically active in the near-infrared regions of the spectrum, right? So there's quite some work being done on developing protocols for fabricating these defects, right, and characterizing them. And then the last part, the last type of candidates that are being looked at, which so like I said in the first lecture, I'm coming from a material science background, so that's one aspect that I find very interesting. There's a lot of people working actually on molecular systems, where you can have these crystalline fields that couple electron spin, nuclear spin, orbital spin degrees of freedom, with optical transitions, right, that you can largely tune by designing your molecules. So I find this a very exciting path, right, because you can use all of your chemical synthesis tools, available tools, to sort of design the quantum states of your system and design what kind of interactions are possible. Right? So the bottom line here that I want to mention is I've focused on the NV for the past 3 lectures. Is the ideal system? Maybe not for a lot of implementations. It's very tempting, it's a room temperature system, it's very tempting for sensing, for instance, and so on. But for quantum communication, for instance, it's not the ideal system. But it is a system that has allowed us to learn a lot about how you can control these degrees of freedom in crystals, right? And what kind of interactions we have access to in terms of sort of expanding or qubit clusters and so on. So I want to finalize with some quick remarks. The first is for me, it's very important to know your qubit, right? And by that I mean understanding its degrees of freedom, understanding what interactions are available to it. That allows you to map quantum circuits into actual physical operations, right? But only when you know what your experimental platform is doing and what you have access to, right? And you definitely need creativity to do that. The second lesson I want to tell you is, for us experimentalists, gate infidelity, it's a very crucial parameter because, like I said, and I repeated a few times, even when we're doing nothing, we're doing something, right? You always need to be talking to your qubit. And then in the material side of things, there's definitely outstanding challenges, right? But doing this work in parallel of exploring what kind of platforms could be useful and developing these protocols on the platforms that we already have at hand, I think that's a good balance of learning how to do this quantum control of these things best, but also looking for solutions for problems that we still have, right? Thank you very much. Thank you for sticking with me.
Thank you, Karen. Questions?
Hello. Carmem, thank you for your lecture. My question is about quantum state tomography. Okay, when you take account the coincidence to build your probabilities to or this matrix, given all the challenges to apply this experimental setup, I suppose this matrix at first time will not be a perfect one in the sense of, okay, will not be trace one, positive standard information. And that's my question. How do you ensure the real physical state? Or how do you transform this practical necessary matrix to a physical one?
The first thing to note here is that, right, error bars are huge, and you're definitely not talking about the ideal case. I think in this experiment, the numbers they have for the events that they collected to these density matrices is on the order of 200, right? So it's still very small n, right? And that's where your large error bars are coming from. So you just, yeah, that's kind of what you have to live with, right? If your entanglement rate is so. In this experiment, so the following experiment, I said the success rate was 1/250 seconds. This was 5-fold worse. Yeah, so 1/1,000 seconds or so. So you only had access to a few entanglement events every day. Right, so that's your challenge, and that's reflected into both the infidelity of these measurements and the large error bars.
I have one question. So it's about his question actually. So because it's not a physical state, right? Because you have these error bars and then you have those satisfy the properties. But do you have some technique, like how to change these to
correct?
Yes, to correct.
I think these are somewhat corrected already.
Okay.
Right, so there are correction mechanisms based on the measurement, but these are already somewhat corrected. Okay. Yeah. And they're all heralded, right? So you're only looking at the subset of measurements that has given you these two counts.
Thank you very much. Thank you very much for this series of talks. I have a bit of a general question. Do you have like a favorite platform that you see most likely to produce an actual usable quantum repeater?
A quantum repeater. I think so. What do you mean? So the question is always, what do you mean by useful, right? Is it the best implementation? Is it going to work on the large scale? My personal feeling is the following: these type of quantum repeaters, they'll maybe one day work on a metropolitan scale, but I don't think not soon anyways. You'll be able to spec them enough to go over the ocean, right? I think that'll be done with satellites. I think it's most likely. In terms of the metropolitan scale implementations, I think I think, for instance, rare earths in solids have demonstrated some very interesting results. These systems, ions, of course. I don't have a clear sort of running contender, but I don't think they'll be used under the ocean anytime soon. At least not these systems. Yeah.
All right, thank you.
So you mentioned moving from nitrogen to silicon and other group 4 elements, but nitrogen is not a group 4 element.
No.
Group 5 element. Why not other group 5 elements? What's the problem with them?
Because you don't. It's the symmetry, right? It's not the element. So if you could have other, I have to say, don't know of other group 5 defects in diamond, but you would likely have a similar electronic configuration to this, or microscopic configuration like this. And what you want to get rid of the symmetry axis. Right? You want to move into a system that has a higher symmetry and that is then more robust to electrical noise. And if you would substitute nitrogen for another group 5 element, I think you would end up with a structure that is more similar to this. Right? So you don't solve your symmetry problem, right? And it's just that the electronic configuration of the group 4 makes it such that the impurity is large enough that it doesn't want to sit in one of the carbon substitutional sites, and it ends up sitting somewhere here in the middle. And it has the right valence to actually bond to the 6 carbons around.
And a related question, but is that also related to the fact that then you have the spin orbit coupling that actually makes you have it cool.
Yeah.
So the two things come.
They're related. Yeah, they are related. So the spin orbit coupling comes from the high symmetry, right? If you would not have the high symmetry, it would largely quench the orbital angular momentum, and then your spin orbit coupling problem is yeah, it's more amenable. So it's the same as these defects that I've studied in silicon carbide. It's a similar thing. You have a high symmetry that gives you orbital angular momentum, and then you have spin orbit coupling, and then right, and then you need to cool down a lot. So they are two.
So it's like a fundamental trade-off. It's not a thing of diamond or whatever. We go to molecules or other structures. You will always have this thing that if you have a symmetry, then you will need low temperatures.
That's not necessarily true,
okay.
right? So if your electronic configuration is such that your ground state is a non-degenerate sublevel, then your orbital angular momentum is quenched, and then you're likely to have large temperature range to play with. The only thing is that in high symmetry systems, it's harder to come across states that are non-degenerate, right? So often you have that trade-off. But you could, so it's not that high symmetry systems cannot have spaces that are non-degenerate, right? There's always at least one space that is non-degenerate. It's just thinking of the correct configuration that stabilizes that space with respect to others that are degenerate. Did that make sense? Yeah.
More questions? Okay, so there's no more questions. Let's thank Carmem.